Hello everyone, this is Andrea Lisiak speaking from Geomechanical. I would like to give you a brief overview of our online course entitled Numerical Modeling of Rock Fracturing Processes. The course will start on October 11th and run for 6 weeks until November 22nd for a total of 50 hours. The course will be taught by myself and my colleague Dr. Omir Mahabadi, and it will consist of a combination of theoretical lectures, practical case studies, and hands-on tutorials using our FDM simulation software Irazu in 2 and 3 dimensions. By attending this course, participants will learn about the basic concepts of numerical modeling for rock fracturing processes, available solutions, their pros and cons, as well as the FDM method. The first part of the course will introduce the topic of numerical modeling rock mechanics, with an overview of the main existing numerical methods and presentation of select continuum and discontinuum or DM methods. We will then focus on the fundamentals of the finite discrete element method, FDM, and its implementation in the Irazu software. The second part will cover fundamental rock deformation and failure processes from both theoretical and numerical modeling perspectives. Several civil and mining engineering application examples will be illustrated, such as damage development around underground excavation and rock slope stability problems. In the third part, we will talk about multiphysics thermo-hydromechanical simulations in the framework of the finite discrete element method. We will focus on theoretical and simulation aspects of coupled problems, including fluid-driven fracturing and thermal-induced rock failure. Finally, the fourth and last part will cover rock support principles and, specifically, grouted rock bolts. Several modeling approaches for rock bolts will be discussed, together with laboratory and field-scale examples, such as pull-out test and rock support and tunneling. We believe that anyone who wishes to use or is considering using numerical methods to investigate rock fracturing, and in particular FDM, will benefit from this course. Furthermore, course participants will receive a free, full-feature versions of Geomechanica's flagship Irazu software for the duration of the course. In this example, we briefly show the model building process for a rock slope stability analysis using the graphical user interface of Irazu. The geometry of the slope is first drawn in the CAD editor by defining the points and lines along the model boundary. Then, the element size for the triangular mesh is selected. A discrete fracture network is defined using the built-in stochastic DFN generator. In this case, 2 joint sets are defined in terms of fracture depth, length, and density distributions. The DFN is generated and the model is meshed. Once the geometry and mesh are created, it is possible to start setting up the rest of the model. This includes the definition of material properties, such as the density, elastic constant, and strength parameters. Built-in empirical relationships are also available to estimate the sum of the fracture mechanics-based input based on other parameters commonly measured in the laboratory. Once the material is assigned to the mesh, the next step is to define the boundary conditions. In the slope example, rollers are applied to the side of the model, while displacement along the bottom boundary will be fixed using pins. Then, the number of time steps of the simulation run need to be specified, together with the time step size and value of the gravitational acceleration. Finally, the mechanical properties of the 2 joint sets are specified and assigned to the previously created DFN. And with this, model setting is complete and the simulation is ready to be launched. After the run is completed, the Irazu user interface can be used to visualize the output and post-process the results. It is possible to visualize the deformation and fracturing process of the slope and contour several field variables such as displacement, stresses, strains, and velocities.